Then let's go ahead and look at review questions that we're technically due today, review questions 3 and 4, and just discuss those. They'll only take a moment. Let me get on the right page here. Review question number 3 says, which of the laws you studied in this module leads to the Kelvin temperature scale? We did that last night. Charles' law. Charles is V1 over T1. So Charles basically discovered that if you lower the temperature to constant pressure, the volume decreases. And that as temperature drives towards zero, one of the things you're going to pick up when we get into the combined gas law, they make the statement just directly. But up until now, we've talked about units. What units can you use, like for pressure, for temperature, for volume? And I've told you before that for pressure and for volume, it doesn't matter, but for temperature, it always matters. For temperature, you always have to use the Kelvin scale. Because think about math. I know it's Monday morning, it's hard, but think about math for just a moment. What happens when you have a denominator? In this case, you have any variable, and you divide it by a denominator. As the denominator gets closer and closer to zero, what happens to the numerator? Or excuse me, what happens to the value of that equation? Let's say x equals 1 over something. If it's 1 over 1, if it's 1 over 2, it's a half, right? If it's a 1 over 1, it's 1. If it's 1 over a half, it's 2. As the denominator gets smaller and smaller and smaller, what happens to the value of the equation? It gets greater, it gets bigger. What happens when the denominator becomes 0? It's undefined, right? We don't really know. We're getting into that theory of philosophy of math kind of thing. Same thing that happens as we get closer and closer to 0. Temperature goes to 0. The Kelvin scale, absolute 0. Volume disappears. Temperature goes to 0. Motion stops. Time stops. We're no longer talking about chemistry. We're talking about pure philosophy. Okay? So, in order to prevent this from happening, from temperature to go to 0, that's why we use the Kelvin scale. If we use Celsius, when would this equation blow up? When would V1 over T1 blow up? If we used Celsius scale. Well, when Celsius is equal to 0. When Celsius is equal to 0, that's the freezing point of water. We can't afford to have temperatures blow up at the freezing point of water, right? We actually want to work around the freezing point of water. If we used Fahrenheit, when would this blow up? Again, at the freezing point of, well, 0 degrees Fahrenheit. It's the negative number Celsius, right? Below the freezing point of water, but still, there's a point where our equation won't work because the denominator would be 0 if temperature were in Fahrenheit. So if it's in Celsius, in the area where we live, if Celsius goes to 0, it blows up. If Fahrenheit goes to 0, it blows up. What about if Kelvin goes to 0? Can we even get there? No, we can't even get there. So think of it very practically. My temperature scale has to be in Kelvin. One of the effects of that is the formulas won't blow up. They won't drive us to an undefined answer because our denominator won't go to 0 because we can't get to 0 degrees Kelvin. We can speculate about what happens at 0 degrees Kelvin, but practically speaking, we're not going to be doing problems where the temperature is 0. So the formulas will work. So when you're using pressures and volumes, as long as you're using the same pressure and volume scale, if one pressure is in atmospheres and you're solving for the other pressure, it's going to be in atmospheres. If one volume is in cubic meters, you're solving for cubic meters. Okay, so pressures, volumes, if you're using torr, it's in torr. Kilopascals, kilopascals. The units have to be the same on both sides of the equation for a V1, T1. In this case, volume could be in any volume unit. As long as I use Kelvin, I'm going to solve for that same volume unit. So pressures and volumes can be in any units as long as they're consistent, but temperatures have to be in Kelvin. Always. Number 4, review question says, what general rule must a careful scientist follow when extrapolating data? was in the reading, will be part of your outline, right? So what is that general rule that we need to use when extrapolating data? The amount is small. Extrapolation, okay. So the amount of extrapolation is small. That's part of the sentence. That's partially true. The extrapolation is small. Pardon? Compared to the available data, right? So it's small compared to what? No? I could say that Austin is tall. Compared to who? You know, if my friend Dave Robinson comes in here, Dave is much taller than Austin. So if I say Austin is tall and Dave Robinson comes in, Austin doesn't look so tall anymore, does he? So tall compared to what? So in extrapolation, the extrapolated data is small compared to the available data. If we looked at the chart, we were looking at absolute zero and this whole idea of volume and temperature, these long lines like that, I have to have a long line of available data which will lead me to make the extrapolation, but the extrapolation has to be small compared to the available data. If I had something like this, I had a very little available data, and based on that, I drew this extrapolation. This is much more likely to be erroneous. Okay? I don't know. This, for all I know, might be part of a curve function. I just happen to hit it during a straight part, and so I extrapolate a straight line, but it's not. It's some other function. But if I have a long available data, and a short extrapolation, then I'm more likely to be accurate. Okay? So that's the point there on the general rule of extrapolating data. I'm going to go ahead and flip back to, let's see, where are we at with lecture? Combined gas law, picking up on page 391. Okay, let's go ahead and jump there. And this will be part of, I'm actually lecturing ahead of your outline. If we follow this on Wednesday, we would have notes through 399. So if you're paying attention in here, you'll get some of. I don't cover everything that's in the book, obviously. I cover the highlights. So as you go through and do your outline, if you haven't already, I know some of you have worked ahead and have this done already, but I'll be looking at probably through 399, but I'll get this out definitively probably through today. Combined gas law, we've already alluded to it here in class. I was talking to one of the students and they said, oh, we've already done that. I said, well, we really didn't do it per se in lecture. We talked about it. We gave 3 different formulas, 2 that we've covered so far, and the combined gas law is the combination of those 2 laws. We talked about Boyle's law. Boyle's was that pressure times volume is a constant, right? Pressure times volume is constant. What's the caveat there? At constant what? Constant temperature. So pressure times volume is a constant at a constant temperature. Boyle. We had Charles. What was Charles' contribution? Said that volume divided by temperature is constant. Caveat there, at constant pressure. Okay, so we've got constant temperature or constant pressure. The combined gas law, well, let's think about both of these. Got the same temperature. Don't let's keep you up. So we have this cylinder has a certain weight on it. And if I increase the weight, which is increasing the pressure, it takes up a smaller volume. Okay? So the force, which is that weight or force divided by the area, is the pressure. That pressure times the volume is constant. So the pressure created here times that volume is equal to the pressure created here times that volume. Or practically speaking, if I put more weight on it, it's going to compress it more. So that's visually how Boyle's law works. The temperature here is constant. In Charles' law, the volume divided by the temperature is constant. How I visualize that is I have the same force pushing down on the volume of gas. But this one over here, I've increased the temperature. Okay, I've increased the temperature. And by increasing the temperature, I have to have an increased volume. Why is it increased volume? Because the volume divided by temperature is the same. The pressure is constant because it's the same weight pushing down on that plunger. That's how we visualize Boyle's law, and this is how you visualize Charles' law. Okay? Now the combined gas law, I'm going to erase all of this. Start by erasing what's over here on the right. The combined gas law takes both of these two and brings them together, and it says that pressure times volume divided by temperature is constant. Okay? Pressure times volume divided by temperature is constant. Let's think about that for a moment. Is there a caveat in there? And I'll just say no, there's no caveat. There's no caveat here that says at constant temperature or at constant pressure. This is true because it includes for variations of pressure, volume, and temperature. Right? They can all change. Let's think about it this way. If I were to rewrite this in a practical way, by that being constant, we would say that P1 V1 over T1 is equal to P2 V2 over T2. That's the applicational formula. That's saying, since it's constant, if I look at it in any instance, it will be simultaneously true then if I change something in the second instance. This is true in both instances. This is something changes between 1 and 2, but the value of PV over T stays constant. Now, written that way, if I were to give you a problem that said, okay, it's in a container that has a certain volume. The gas we're looking at is in a container, a metal container. The volume is not going to change because the metal container is not going to suddenly blow up get bigger like a balloon and collapse. So if you have a constant volume, a volume that does not change, normally that's in a cylinder. A cylinder is not going to change its volume. What does that mean? If the volume is the same, well then V1 and V2 are equal. So if V2 is equal to V1, I can eliminate it from the equation, and then I know I'm only looking at pressures and temperatures. You see that? If you're working a problem and it says it's going to be at a constant temperature, well, if T2 is equal to T1, I can eliminate that from consideration, and I'm just left with P1 V1 over P2 V2. And lastly, if pressure is constant, that means that P2 is equal to P1. I can eliminate that from consideration, and now I have V1 over T1 is equal to V2 over T2. Oh, but look we already know that at constant pressure, V over T is constant. Well, guess what? There it is. And here, Boyle's law, when temperature is constant, P times V is constant. It's right there. See that? So if we understand the combined gas law, PV over T is constant, we can derive Boyle's law and Charles' law. Why? Because the combined gas law comes from combining Charles' law and Boyle's law together. So when they make the caveat at constant temperature, you could derive it by taking PV over T and eliminating T as being constant. And when you have Charles' law, V over T is constant, you can use the combined gas law, but write it with P being constant means it drops out of the equation, and then you've got V over T as constant. So the combined gas law is Boyle's law and Charles' law combined. And when you take into account the constants, the formula rewrites as the individual laws. And when they're all variables, you just use the straight PV over T as constant. Let's go ahead and use this a few times, and we can do this looking at example 11.1, page 392. Okay? So let's just walk through a couple of these examples together. Example, and the way I would encourage you to do it on your paper, same way I do it here. Gas law, I assume that I'm going to have a P, a V, and a T in two instances. So keep them together, P2, V2, and T2. I'm assuming I'm going to have that information. That's where in the module, plus for most gas problems, I assume this is what I'm going to need. So let's go ahead and read it. A weather balloon is filled with helium before it's launched. Okay? Before it's launched on the ground. So on the ground, the gas has a temperature of 25 degrees Celsius and a pressure of 1 atmosphere. The volume of the balloon is 4.5 meters cubed. As the balloon rises, the pressure and temperature change to 0.30 atmospheres, (15°C). What is the new volume? Okay. It's just reading the word problem, extracting the information we need. Given P1, V1, and T1, and P2 and T2, solve for V2. I'll write my formula. P1 V1 over T1 is equal to P2 V2 over T2. I need to rearrange that formula to solve for V2. So what does V2 equal? It's going to be P1 V1 T2 over T1. P2. Is that right? I've got what I'm trying to solve for right here. And because it's pure multiplication, I can slide that to the top, slide that to the bottom. Okay. Now, before I go plug anything in, do I need to convert anything over here? I have pressures in atmospheres. I've got a volume in cubic meters. I've got temperature in degrees Celsius. I've got temperatures in degrees Celsius. I've got temperature. Okay. Temperatures have to be in Kelvin. Right, we just talked about that. Temperatures have to be in Kelvin. Pressures can be in whatever. They're both in atmospheres. Good. It'll work. Volume, 4.5 meters cubed. We're looking for the second volume. When we solve this, what is our unit of volume going to be once we do the numbers? It's going to be meters cubed. It has to be the same units, same units. Same units here, but these units have to be Kelvin. It's the only one that has a stipulation on it. So we need to convert both of these to Kelvin. We do that by 273.15 plus the degrees Celsius. Now we can only take it out to, with precision, right, we're adding. This one is only as precise to the units, so we can only take it to the units. That's why it's 298 and not 298.15. See that? Addition, subtraction, you can only be as precise as the least precise. The least precise here is 25. T2. Plus 15, 288. Okay. That's why they have 298 and 288 Kelvin. Why? It's 273.15 plus degrees Celsius, precision to the least precise. If it had been 15.0 degrees, then it would be 288.2. But since it was only 15 and 25, we can only take it to the ones place. So 298. So now that it's in the appropriate units, now we can come over and plug it into the formula. The V2, the P1, come over your table here, is 1.0 atmospheres. V1 is 4.5 meters cubed. T2, 288. Now I put the coefficients here, 1.0, 4.5, and 288. I'll bring all the units out to the right-hand side. So the 1 atmosphere times meters cubed times Kelvin, and we're going to divide all of that by T1, P2. T1, 298. P2, 0.30. And the units are Kelvin atmospheres. Okay? 298 Kelvin, 0.30 atmospheres. Look at it real quickly, go through and cancel my units. Kelvins cancels kelvins, atmospheres cancels atmospheres. My remaining units are meters cubed. I'm looking for volume. Does it make sense that volume would be in meters cubed? Yes. So I know my setup is right. I go through and do the math. The book says the math for this works out to be 14 cubic meters. And again, this problem is all worked out there on page 392. This is a way to set it up with your base information right there and your formula using the combined gas law. Okay. So any questions on extracting the information? Pretty straightforward from the text, hopefully. Writing down your, usually going to be the combined gas law formula. Converting temperature to Kelvin. Temperatures always have to be in Kelvin. Plugging the information into the rearranged formula and doing the math. Go ahead and erase. Let's look at the second part there on 393. It's another gas problem, so P, B, T. You guys should do really well on all these gas problems. Okay, anyway, help them with that later, will you, Austin? Gas is stored in a 3-liter container. Say 3.00 liter. Okay. At a pressure of 456 torr. If the temperature stays constant, what will the pressure of the gas be if the volume is decreased to 0.75 liters? Okay, let me read it again. Okay. A gas is stored in a 3-liter container at a pressure of 456 torr. If the temperature stays constant, T2 is equal to T1. What will the pressure of the gas be if the volume is decreased to 0.75 liters? Okay. Which of our laws was based upon the requirement that temperature remain constant? Boyle's. What did Boyle's law say? That pressure times volume is equal to pressure times volume, right? That's Boyle's law. If temperature is constant, P1V1 is equal to P2V2. Now, if we wrote down the combined gas law, if we didn't remember that, if we wrote down the combined gas law, and we said that P1V1 over T1 is equal to P2V2 over T2, and I remember that T2 is equal to T1 because it says the temperature doesn't change, right? The temperature stays constant. Now I know that they cancel out, and so I'm left with Boyle's law. Also, since temperature is constant, we don't have to convert to Kelvin. Doesn't matter. Doesn't matter what the temperature is. It's constant. So we're purely using Boyle's law right now. So P1V1, pressure 1, 456, V1, 3.00, equals P2 times 0.75. So solving for P2, and the book says 1.8 times 10 to the third. What would my units be? What's my pressure units here? Because they were in torr, my answer is in torr. Okay. Go ahead and let's go ahead and try 11.1 on your own into your notebook. Okay. On your own 11.1. I'll give you a few minutes to get your numbers extracted from the text, then I'll go ahead and start doing it on the board with you. A gas is stored in a metal cylinder with a volume that cannot change. The gas is packed into the cylinder at a temperature of 5 degrees Celsius under a pressure of 3,150 kilopascals. What will the pressure inside the cylinder be when it is stored at 30 degrees? Obviously, we need to make sure that whatever cylinder it's in, that the walls of the cylinder and all the joints can handle that amount of pressure. So. Good. Okay, thank you. So, caught an error here. So it's 303. Okay. Anything else? Good. Okay, so you have to get on the right page.
I have to do this one.
Nope, we're on your own. That's what we finished in class. That's what we're doing right now.
Wow. Not bad.
Yep. Today?
Yeah. Every
We're going to limit it to today?
every now and then.
Okay.
No wonder I was wondering how you got that first number. So I was sitting there just thinking about it.
Just so you know, you're sitting there thinking about it looks remarkably like you sitting there not thinking about it. Just so you know. Let's take a quick look at 11, 2, and 3. Just to see if we can convert the word problem into the variables we need to look at, okay? So again, assuming it's a gas law problem, P1, V1, T1, P2, V2, T2. All right. So at room temperature and normal atmospheric pressure, so let's assume it's going to be our first instance, okay? At 25 degrees Celsius and normal atmospheric pressure, the average person's lungs have a total capacity of about 5.5 liters. If a man takes a deep breath, so you fill your lungs to capacity, and then dives deep into a lake where the temperature is 17 degrees Celsius, and the pressure is 895 torr, what is the new volume of the air in the lungs? Hopefully you can see that's, P1 V1 over T1 equals P2 V2 over T2. We're solving for V2, so it'd be P1 V1 T2 all over T1 P2. Okay, so just rearrange the formula solving for the unknown, the second volume. Now what other trick is there? We got two things we have to do before we can use this information. We have to convert Celsius to Kelvin, right? So we're going to add 273.15 to both of these. They're only accurate to the ones, or excuse me, to the tens place. 17 degrees and 25.0 degrees. Yeah, so since those are out to the tenths place, we can take it out to 273.15, add that to it, and take those answers out to the tenths place. So converting temperature to Kelvin is the first thing. What's the other thing? Pressures are in different units, right? So we need to we need to get them in the same units. How can we do that? Well, they make this easy for you. They say it's 1 atmosphere, right? What is 1 atmosphere in torr? 1 atmosphere in torr is the same number of millimeters of mercury, right? 760. So you know that 1 atmosphere is equal to 760 torr. So you could also write this as 760 torr and use that 760 and 895. So keep it using torr for pressure, degrees Kelvin for temperature. My volume is going to be in what units? In liters when I use that formula. Okay. If they didn't give us 1 atmosphere, it would be some proportion of an atmosphere, right? Let's say it wasn't 1 atmosphere. Let's say initially it was given to us as 0.8 atmospheres. If I need to convert 0.8 atmospheres into torr, how would I do that? Well, my unit multiplier would be 760 torr is equal to 1.0 atmospheres. Right? This is my statement of equality. 760 torr is equal to 1 atmosphere. If I have 0.8 atmosphere, if I do that math, it's going to give me an answer in torr, and I could use that in my problem. Okay. And lastly, 11.3. Let's just extract the information we would need out of that. Let's see what they have for us. 11.3 says, let's see. If you fill a balloon with air to a volume of 3.21 liters at a temperature of 22 degrees Celsius, what volume will the balloon have if it is stuck in the freezer assume the pressure stays constant. We could use combined gas law. We also know another law that doesn't include pressure. At a constant pressure, right? What's that law? Charles' law? V1 over T1 equals V2 over T2 at constant pressure. So whether you wrote the combined gas law out or just went straight to Charles' law, what do we have to do here? Convert both of these to Kelvin, right? And your answer will be in liters.